Hello viewers, welcome to my YouTube Anjane Maths channel. In today's video, we are going to study the quantifiers, quantified statement in a logic, negation of quantified statement, inverse, converse and contrapositive of a conditional statement. So to understand the quantifiers, I shall consider the two examples. So the example is there exists an even prime number in the set of all natural numbers. Second example, all natural numbers are positive. So if you observe these two statements, in these two statements we can see the words like there exist and all. So the words like there exist, all, or for all, such words are called as quantifiers. Now here the word there exist is known as a existential quantifier, denoted by the symbol. Read it as a there exist. Whereas the word all or for all is known as a universal quantifier, denoted by the symbol like this. Read it as a for all. Then what is quantified statement? Statement involving the quantifiers are called as the quantified statement. Every quantified statement corresponds to the collection and the condition. Or in other words, we can say that every quantified statement is the combination of a collection and a condition. Now if you see the first example, there exists an even prime number in the set of all natural numbers, which is a combination of the collection and the condition. Now in this case, what is the collection and what is the condition? Set of all natural numbers is nothing but what? The collection. And being an even prime number is nothing but what? The condition. Whereas if you see the second example, all natural numbers are positive. In this case, what is the collection? Collection is nothing but what? All natural numbers. And what is the condition? Positive number. When the quantified statement will be true, the quantified statement containing a universal quantifier is true if all the objects in the collection satisfies the condition. And if it fails, if at least one object in the collection does not satisfy the condition. And when the existential quantified statement will be true, a quantified statement containing existential quantifier is true if at least one object in the collection satisfies the condition. And it falls if no object in the collection satisfies the condition. Now let us take one example. If set A equal to 1, 2, 3, 4, 5, 6, 7. Determine the truth value of the following quantified statements. So the first example, there exists x belongs to A such that x minus 4 equal to 3. Existential quantifier. Second example, for all x belongs to A, x plus 1 is greater than 3. Universal quantifier. For all x belongs to A, 8 minus x is less than 7. Universal quantifier. Fourth example, there exists x belongs to A such that x plus 8 equal to 16. So the solution is like this. So take for x is equal to 7, there is at least x belongs to A such that x minus 4 equal to 3. That means among this set A, if you choose any value, that value of x must satisfy the condition. Okay, say if, I will choose that x is equal to 7. The equation is x minus 4, that is equal to 7 minus 4 equal to 3. That means for x is equal to 7, the condition is what? Satisfies. Therefore, x is equal to 7 satisfies the equation. Therefore, we can say that the given statement is true and its truth value is what? T. Take the solution of second example. For all x belongs to A, x plus 1 greater than 3. For all x belongs to A means what? If you take any value of x from this set A, that value of x must satisfy this condition. So let us begin with, say, x is equal to 1. Find the value of x plus 1, that is 1 plus 1. So x plus 1 equal to 2 we got. Definitely which is not greater than or equal to 3. The condition what? X, the value of this should be greater than 3. But here we got a 2. Definitely it is not greater than or equal to 3. So for x equal to 1, x plus 1 greater than 3 is not true. Therefore, the truth value of a given statement is a false. Take the solution of next example. For all x belongs to A, 8 minus x is less than 7. What is the meaning of this? So if you take any value of x from this set A, that value of x must satisfy this equation. So if I take x is equal to 2, 8 minus 2, that is nothing but what? 6, definitely less than 7. If you take x is equal to 3, so 8 minus 3, 5, definitely less than 7. If I go for x is equal to 4, 4 minus 4 is 4 only, again it is less than 7. So if I take x is equal to 5, 8 minus 5, you will get 3, less than 7. If I take x is equal to 6, 8 minus 6, 2, less than 7. If I take 7, so 8 minus 7, you will get 1. So definitely less than 7. That means for every value of x, it satisfies the condition 8 minus x less than 7. Therefore, the given statement is true. Its truth value is what? T. Take the solution of fourth example. There is x belongs to A such that x plus 8 is equal to 16. That means in this set A, there is one value of x which satisfies this equation. So if you observe these values, so if I take the maximum value of x among this the set A, that is 7. If I put this x is equal to 7 in place of x here, what will get? Say 7 plus 8, you will get 15. What it means? It means that there is no value of x in the set A which satisfies this equation. Therefore, the given statement is what? False. Therefore, its truth word is what? If. Next, I am going to consider negation of quantified statement. What is the rule behind this? The negation of quantified statement is obtained by replacing the word all by some and for every buyer there exists, and vice versa. Means what? Or replace the word there exists buyer for every and some buyer all. Now let us take the examples based on the negation of quantified statements. So the first example is like this: all natural numbers are integers. So we know that to write the negation of the quantified statement, the word all is replaced by what? Some. Then its negation is given by what? Some natural numbers are not integers. Since it is the negation, you should add the word not in a proper place. Some natural numbers are not integers. Take the next example. Some students of class 12 are 18 years old. Now to write the negation of this quantified statement, the word some is replaced by what? All. Then its negation is what? All students of class 12 are not 18 years old. Take the next example. For all n belongs to n, for all n belongs to n plus 7 is greater than 8. So what type of quantifier is used here? For all. For all or for every. Then to write its negation, for all is replaced by what? There exists. So its negation is what? There exists n belongs to n such that n plus 7 is less than or equal to 8. So this is the negation of this statement. Take the next example. There exists n belongs to n such that n plus 4 is greater than 9. So the existential quantifier is used. So that there exists is replaced by what? For all. So the negation is what? For all n belongs to n plus 4 less than or is equal to 9. So this is the negation of this quantified statement. So next I am going to consider converse, inverse and contrapositive of implication or conditional statement. So the converse, inverse and contrapositive can be written only for the conditional statement, only for the implication. Try to remember the rules of converse, inverse and contrapositive. See, if P and Q are any two statements, then the symbolic form of the implication of the two statements P and Q is denoted by what? P implication Q, P conditional Q. Then what is the condition of converse? Converse of the conditional statement P implication Q is defined as Q implication P. Q implication P is the converse of P conditional Q. Then how the inverse is defined? Negation of P implication negation of Q is the inverse of the conditional statement P implication Q. Then contrapositive is defined as negation of Q implication negation of P is the contrapositive of P implication Q. Now let us take the example based on converse, inverse and contrapositive of a conditional statement. The question is like this: write the converse, inverse and contrapositive of the following statements. So the example is what? If a function is differentiable, then it is continuous. So if then connective is present, so it is what? A conditional statement. Now let us split this given conditional statement into two simple statements. So let P a function is differentiable. Second simple statement, say Q, it is continuous. So then the given conditional statement in its symbolic form is what? P conditional Q. That is nothing but if a function is differentiable, then it is a continuous. Then let us define the converse. What is the definition of converse? Q conditional P. Then into its word form, it can be written as, if a function is continuous, then it is differentiable. Exactly reverse of this. If a function is continuous, then it is a differentiable. Then what is the inverse? Negation of P, conditional negation of Q. How it is stated? If a function is not a differentiable, then it is not a continuous. Negation of P is what? A function is differentiable. Its negation is what? A function is not differentiable. What is Q? It is continuous. Its negation is what? It is not continuous. So negation of P, conditional negation of Q is what? If a function is not differentiable, then it is not a continuous. Then contrapositive. How it is defined? Negation of Q, conditional negation of a P. What is Q? It is continuous. What is its negation? It is not continuous. What is P? A function is differentiable. What is its negation? A function is not differentiable. So then contrapositive is stated as, if a function is not continuous, then it is not a differentiable. Take one more examples on converse, inverse and contrapositive. The conditional statement is like this. A family becomes literate if the women in it are literate. So let us split this conditional statement into two simple statements. Say statement P, the women in the family are literate. Statement Q, a family becomes literate. Then the given statement in the symbolic form can be written as P conditional Q. If the women in the family are literate, then a family becomes literate. Now I'm going to write the converse of the given conditional statement. The converse is defined as Q conditional P. If a family becomes literate, then the women in the family are literate. Take the inverse, defined as negation of P, conditional negation of Q. What is P? The women in the family are literate. Then what is its negation? The women in the family are not literate. Then what is Q? A family becomes literate. What is its negation? A family does not become literate. So therefore the inverse of a given conditional statement is stated as negation of P, conditional negation of Q. If the women in the family are not literate, then a family does not become a literate. Now come to the next step, contrapositive, which is stated as negation of Q, conditional negation of P. So if a family does not become a literate, then the women in the family are not literate. So this is the converse, inverse and contrapositive of a given conditional statement. Now let us consider algebra of statements. Some laws are there which you have to remember it very well. So the first law, idempotent law, P conjunction P is always equal to P, or P disjunction P is always equal to P. Second commutative law, P disjunction Q is equivalent to Q disjunction P. The same law we can write in terms of conjunction. P conjunction Q is logically equivalent to Q conjunction P. Then associative law, P disjunction Q disjunction R is logically equivalent to P disjunction Q disjunction R. Same law can be written in terms of conjunction. P conjunction of Q conjunction R is equal to P conjunction Q conjunction R. Distributive law. Distributive law, which is nothing but the combination of disjunction and conjunction. So for example, if I take this A into B plus C, can be read as what? A into B plus A into C. Same rule you have to apply for this distributive law. So P disjunction Q conjunction R is logically equivalent to P disjunction Q conjunction P disjunction R. Or if you reverse that, disjunction becomes conjunction and conjunction becomes disjunction. So P conjunction of Q disjunction R is logically equivalent to P conjunction Q disjunction P conjunction R. Then De Morgan's law. If you take the negation of conjunction of the two statements, conjunction changes to disjunction, and you have to write the negation of each statement. So that is negation of P conjunction Q equal to negation of P disjunction negation of Q. Same rule is applicable in terms of disjunction. Negation of P disjunction Q is equal to negation of P conjunction negation of Q. Disjunction changes to conjunction. Now the next law is what? Identity law. P conjunction T is equivalent to P, or P conjunction F is equivalent to F, or P disjunction F is equivalent to P, or P disjunction T is equivalent to T. Now complement law. P conjunction negation of P is equivalent to F. P disjunction negation of P is equivalent to T. Then absorption law. P disjunction of P conjunction Q is logically equivalent to P. P conjunction of P disjunction Q is logically equivalent to P. Then conditional law. P conditional Q is logically equivalent to negation of P disjunction Q. And finally, biconditional law. P biconditional Q is logically equivalent to P conditional Q, conjunction Q, conditional P, or logically equivalent to negation of P disjunction Q, conjunction negation of Q disjunction P. So you have to remember these laws very well. Now after this we are going to work out some examples based on these laws. The question is like this: without using truth table, prove that P biconditional Q is logically equivalent to negation of P conjunction negation of Q, conjunction negation of Q conjunction negation of P. So let us consider its left hand side, that is P biconditional Q. So by biconditional law, this can be written as P conditional Q conjunction Q conditional P. Then we use the conditional law for these two statements. So this P conditional Q can be written as negation of P disjunction Q, conjunction as it is. So again negation of Q disjunction P by conditional law. Now by De Morgan's law, apply negation to this. So negation of P conjunction negation of Q. So in De Morgan's law, the disjunction changes to what? Conjunction. And you have to take the negation of each statement. So here negation of P will get P, and negation of Q becomes a negation of Q, conjunction as it is. Again you apply the De Morgan's law, take the negation of this. So when you take the negation of this negation of Q disjunction P by De Morgan's law, negation of the first, disjunction changes to conjunction, take the negation of P. Negation of Q is what? Q conjunction negation of P. So you will get a F. So negation of Q conjunction negation of P. So this is nothing but what your right hand side. So this is the proof without a truth table. So by using the algebraic laws of statement, we have proved this. Take the next example. Negation of P disjunction Q, disjunction negation of P conjunction Q is logically equivalent to negation of P. So without using the truth table, we are going to prove this. So let us begin with the left hand side. So negation of P disjunction Q, disjunction negation of P conjunction Q, that is equal to, so apply the De Morgan's law to the first bracket. So what is the De Morgan's law? So negation of P disjunction Q is in case of, if you take the negation of the disjunction, the disjunction changes to what? Conjunction, and you have to take the negation of each statement. That is what? So this is De Morgan's law. So according to this becomes what? Negation of P, conjunction, negation of Q, whereas the remaining part I wrote as it is. Now the next step, the distributive law. So what is the distributive law? See here, A into B plus A into C. Then we can take here A into as a common. So A into as a common means what? B plus C. Like that. So if you see here, so this negation of P conjunction, negation of P conjunction is a common. If I take common, what will remain here? Negation of Q, disjunction of Q. So by distributive law. Then what is negation of Q, disjunction Q? It is T. By complement law, what is complement law? Negation of P, disjunction P is what? T. So like that it is what? T. Then again by using the identity law, P conjunction T is what? P. So negation, if I consider this way as P conjunction T is P, then negation of P conjunction T is what? Negation of P. So that is nothing but your right hand side. So this is the. Now take the next step of example. The question is like this. Rewrite the following statements without using if then. So the example is like this. If prices increase, then the wages rise. So let us split this conditional statement into the two simple statements. Statement P, prices increase. Statement Q, the wages rise. So therefore the symbolic form of the given statement is what? It is P conditional Q. Now you have to rewrite this without using a if then. So we know that by using the conditional law, P conditional Q is logically equivalent to what? Negation of P, disjunction Q. Now you have to write its verbal meaning. So now you have to write this in a sentence form. Negation of P is there. What is P? Prices increase. Its negation. Prices do not increase. Disjunction means or. Statement Q, the wages rise. So without using if then, we have written this statement. Take one more example. If it is cold, then we wear woolen clothes. Now we split this conditional statement into the two simple statements. Statement P, it is cold. Statement Q, we wear woolen clothes. So the given statement in its symbolic form is what? P conditional Q. But we know that P conditional Q is what? Logically equivalent to negation of P, disjunction Q. The given statement without if then can be written as first upon negation of P. P is what? It is cold. Its negation is what? It is not cold. So it is not cold. Disjunction means or. Q, we wear woolen clothes. So we are represented the given conditional statement in terms of what? Without if then. So in today's class, we have seen that quantifiers, quantified statements, negation of the quantified statement, converse, inverse, contrapositive of a conditional statement, and the algebra of statements. If this video is really helpful for you, then you please like it, share it, do the comments, and subscribe the channel.